My name is Jason Smith from Absolute EMC. Today we're going to go through a little bit about the MGA 1033 from Schroeder. This unit is pretty incredible in how many standards it can be used to test to and its capability. The testing that it performs covers the audio frequency range in the DC to 250 kilohertz range to do radiated testing for magnetic immunity, conductive immunity, and as well as emissions testing. This unit contains everything that's needed to do the testing. That has the amplifier, the signal generation, and the measurement part of it. So we're going to go a little bit through what's included and what you get with the system. Thanks. All right, so I'm going to go through a little bit of the front panel here. The unit has some inputs, a voltage input for connecting a magnetic loop sensor or maybe a current loop sensor that measures from a voltage difference, and also has a current input for measuring current. We have here different outputs for different loops. We have the capability of doing a 3-axis Helmholtz coil and automatically switching between all the axes. But in most cases, you use a single axis loop antenna, which that would come out of the X1 position. There's also a 50 ohm output here for doing testing which requires 50 ohms on the amplifier output. And that's the power on and off. Give a protection when overload happens, a ready light, and then of course when the light is on for the 50 ohm output. We have a ground stud to connect the generator to ground to have a nice ground reference. All right, so we go back and through the back side of the generator to show the different connections here. We have a USB connection to go to the computer, some USB loop through connections so you can connect other peripherals to the system. The added input, this one in particular, is used for the Hall sensor for doing DC measurements. A multimeter input for doing EUT monitoring if you have that. External input for driving the amplifier with an external source, high impedance source. We have a loop back, the generator output to the amplifier input. We have a second output for the generator, which could go to another amplifier if needed. A trigger input. If you need to trigger your testing to match up with something. There's a scope function inside as well, the unit, so you can trigger that. And an EUT fail in. So you can monitor your EUT. Here we have our power connection for the generator. The power plug is a locking plug, so it sticks in and it stays secure. The USB connection on the back side here goes in and locks in, and then we have a Hall sensor here which connects to the back. Add input. Along with other accessories, we have all the calibration and software on a USB drive. This is your loop sensor for doing radiated magnetic emissions, as well as setting your levels with your loop. There's a cable for connecting the loop, radiating loop antennas. These are two commonly used radiating loop antennas. This is an RL120. This is commonly used for a lot of military standards and automotive standards for immunity testing. And this is the RL120-80. This is a bigger coil with more turns on it to do low frequency DC testing and low frequency testing in the hertz range to get a higher field. There's some additional accessories not commonly used, but come along with the system for more ease of use. There's a 100 ohm impedance which adds to the radiating coil to allow for lower level testing. There's some standards that have some low level magnetic tests that in order to reach those levels, we have to put some more impedance in there and to help with the measurement system inside the generator. There's a cable to connect to a BNC measurement. If you had a different loop sensor, you could use this for that. Or if you had a current probe for measuring conducted emissions, it would connect with that cable. And some patching cables to be used as well if needed. So we're going to hook up the front with some measurement and radiating loops. So first we're going to hook up the radiating loop, take basically the color codes of the inputs here and go into X1. The other side of that cable, we're going to connect to our higher frequency radiating loop. It's hard to do this with one hand while I'm holding the phone. There we go. So in the radiating loop, on the one side there, we have a 5 centimeter standoff. That's commonly used in many standards. When you're testing a product, say this was the EUT we're testing or DUT, that gives you the 5 centimeters standoff. All right, now we're going to connect our loop sensor, the LS40. Just plug it into the front here. And this nice convenient connection here, it just goes around our standoff. And so it puts it in a nice, perfect position, easy to use. So that's our front connections. Get this out of the way, that over there. Now we can turn on the system. And I'll boot up and everything will come through, and when it's ready, the ready light will come on. There we go. We can start the computer here. And we can boot up our MGA software. Now turn on the software. Some minor clicking happens inside the generator. You know it's connected and working. So the system is connected through the USB connection. And that's our opening screen. So up here you have a couple different selections of where you need to go. So we're set up to do a radiated magnetic immunity test. So we call them the magnetic field tests. And we have standard measurement, standard generation, continuous generation, and short-term generation. Standard measurement, which means you're going to measure emissions. Standard generation means that you're going to generate a field. So first we're going to do that. Do a test, and then here it's going to come up and ask for a standard to run. All right, we go to standard, and we'll start with, say, Navy. Okay, you just need to select one actually to start off with, and we can change this and save it as a different name as needed. So it's saying it needs a cal file, just means that we haven't run any tests yet. Okay. So we have here, the red line shows our maximum available level. Oh, there's Windows jumping in there. That we can put out. The yellow line is the standard that's defined over on the left here. And then the blue line is our minimum field we can generate. Right now we have the coil set for the RL120, that's what's hooked up. We have the RL120 with the resistor, and we also have the low frequency RL120-80 in here. So we have the ability to change units from dB picoteslas, amps per meter, dB microamps per meter, or microteslas. If we do that change, so we go to amps per meter, everything changes to amps per meter in the graph and over the left. So it automatically changes all the units. Let's go back to what the standard requires. You also can change your frequency steps, whether it's log or linear. You have the choice between current calibration by coil data or current calibration according to ISO 11452-8. So per these requirements, the coil level or the field that's generated by that coil is set directly by the current. It's pretty much a straightforward, no matter what frequency or test you're at, or the level at, the current is directly proportional to the field generated. Doesn't matter what frequency, but ISO 11452-8 requires a full calibration across the frequency range, which is perfectly fine. It can be done, or you can just go by the calculation of the coil, which saves a little bit of time if it's allowed. You also have the ability to do a simple modulation with AM 1 kHz 88% modulation. That's a requirement in one of the EN standards. So we're going to do the current calibration so we can see something happening here. So we could save that, or we'll just go back to the test here. So now we're back to the test window. In the test window, we can put in some information about the DUT in the test if we want to, which basically just go into general statement here, and we can add our own statements in there. The calibration, we sit there and we pull up the loop sensor that we're going to use, which is the LS040. And we're going to do what's Windows doing now. You have a choice between a field verification and a field calibration. A field verification just checks at one frequency, and a field calibration does a whole frequency scan. So to bring that up, it tells us to put the loop sensor in the X dimension, because that's what we're going to connect. That's what's set in the setup. We have our setup here with the loop and the loop sensor. Okay, so we're running our field calibration with our loop sensor and our transmit loop. The green line is showing the target level of the field, and that's on this axis over here, and the red line is showing our current level that we're measuring, and that's on this axis here. Additionally, we have what frequency we're at, the current that's actually measured, the mag field that we're shooting for, the key for the different colors, and then of course you have the frequency on the bottom. And all the information is there, with what standard, what loop sensor, and what drive coil or gain coil we're using. This is where we have it, because I did one earlier. And once we have that, we can set up our loop on the DUT that we're testing, or EUT, and hit start sweep. And here it's going to turn it on and getting started. And this window is basically just showing what steps we're at. So we're at the frequency, what test level it's measuring. We can, before we run the test, also make some modifications by upping the test level. Say we want to do some margin above or some margin below. We can change what axis we're testing. We can narrow the start and stop frequency range, and we can change our steps sizes. Right now we're at 10 steps per decade, and we can change our dwell times. We're doing 10 seconds per frequency. And some more things we can go over here. So in sweep, all the other things are grayed out while we're doing a test. We can break a sweep. Click on that. So it tells us what frequency we're at, what level we're at. We can turn the output on or off. We hit OK and it'll continue. Or we can abort it. We can abort the sweep. We can turn on a signal at sweep end so that you don't fall asleep when it ends. Pretty much going through different test levels and the frequency. So we'll abort this. So you have the ability to go to any frequency you want to in this range. Say we wanted to go to 2 kilohertz. You can hit return. So it picks the closest step to 2 kilohertz, and we can turn it on. And so we can do a test manually as well to double check certain frequency ranges. Now we're going to show how to run a test for a single frequency at a time. This is normally used for the low frequencies when you have to dwell for a little bit of time. You can do one frequency at a time in the DC range and low frequency hertz. So to do that, first we're going to do is change the setup a little bit. So right now we have the higher frequency loop and loop sensor hooked up. What we're going to do is switch to the larger loop. Let's move the connections over. So for this, we're going to use the Hall sensor. So this is the Hall sensor. We put that in and connect it for doing DC testing and low frequency hertz. Let's move this other stuff out of the way. Okay. Alright, get set up here. To do a continuous generation. That'll be basically a single frequency test. And in here you can do the same print setup to put in your device information. We want to switch our transmit loop to the -80. And we can turn on connect our loop Hall sensor. Connect that up. Oh, we have to do one thing first. Let's go back. We need to change the frequency to a low frequency. Let's go 1 hertz. Now, loop Hall sensor. There we go. Now we got the Hall sensor comes up. And we can change the test level we're going to do at. Say dB. Let's go 186. We got 1 hertz set up, 186 dB picoteslas. We're on dimension X, so we could hit and turn on the field. Turn on the field. This light indicator comes on. But are we doing the right field? We do. It's calibration, field verification. There we go. So right now it's measuring the field verification from the Hall sensor. Okay. And now we can take that Hall sensor off and do the test on our product for 1 hertz. And we can just change the frequency to 2 hertz. Current regulation. We want to verify that again. There we go. Now to do a DC test, turn this off. And we'll go here and switch our testing to DC. And there, so we're at 0 hertz. And basically have the same setup. Turn that on. Field verification. And we're at 186 dB picoteslas. And then we can do our testing at DC.